Assalamu alaikum. My name is Farzin Khan and my group members are Idris and Abdul Sabur. We will be discussing about identifying optimal passing pattern using temporal subgraph isomorphism for football teams. As for our project requirement, first we have to describe the problem solved by Oberoi and the teams. Oberoi and his colleagues focus on detecting dynamic patterns in evolving graph using subgraph isomorphism. Unlike static graph, dynamic graph evolve over time, making the detection of recurring patterns computationally challenging. Their method models graph as sequence of snapshots capturing discrete time interval to facilitate efficient pattern detection in dynamic systems such as social network or biological system. As we can take the example of football, uh, during football match we can take the player as a node and their passes as an edge in the start and end of the game. There are patterns are created in which the start and uh, end of the game patterns of edges is not equal. So Oberoi gives us the solution by identifying optimal pattern using isomorphism. The second requirement was how the solution proposed by Oberoi and team is different from previous work. As the previous work were based on static models, therefore the Oberoi and his teams proposed a model which were based on basically dynamic. Previous method focused on static patterns or aggregated time span models to study temporal challenges. Oberoi team introduced snapshot-based approach where each snapshot represents a static state of graphs. While the third requirement was provide the evidence that Oberoi's team's work to show that solution is better than the others. For the evidence, the team benchmarked their algorithm against two state-of-the-art methods using real-world data sets from telecommunication and bioinformatics, resulting demonstrate competitive execution times and superior performance in scenarios where aggregated models fail to capture temporal nuances. This method excels in application requiring high temporal precision and snapshot fidelity. Now Idris will tell us about the execution, input and output of the code.
In the code implementation and execution, we see that there's a dynamic graph subgraph detection, and in which we take the two graphs as an input, the graph G, a dynamic graph, the larger graph, and then the graph H, a smaller subgraph, right? And our objective of this, the code is we take the input and we check that if the H exists at the subgraph in the G, right? And we will verify that there exists a valid mapping between the vertices and the edges of the H and G. So for the mapping of the vertices, an algorithm that tries to map the vertices in the H to the vertices in the G while maintaining the graph of the structure. Like of the we see that in the edge relationships, right? And the second of the edge verification, we see that along with the vertices, the corresponding edges in the H are checked for the existence in the graph G, right? And the output of the graph and the output of the code represent as the display of the vertices mapping from all of the valid subgraphs in the H and G, the total number of the valid subgraph, and the time that it takes, right? So let me show you. Okay, so here if we see that that we take the inputs, the series of the inputs, and we get the output, the number of the correct relations that are formed, and the time that is taken. So uh, we see the valid subgraph, the algorithm that finds the instances where the H lies in the subgraph within the G, the vertex of the mapping of the vertices, and from the graph H to G as we see in the output, and the performance matrices, the total subgraph formed, it shows the count of the possible embedding of the graph H and G. In we see as the number of the solution of the graphs, and the time it takes, that displays the time that taken for the execution of these graphs. So the key highlights of this the code is a comprehensive approach to make the to match the vertices and the edges between the graph and the subgraph H and G, and optimize to analyze the large graphs effectively while ensuring of the correctness.
Hello, our topic is the my topic is the summary of paper, which is of Bernoulli's, is how basketball teams passing behavior affect their performance using a model called temporal passing network model, TPNM. This model studies how player passing interaction over the time creates a network and how the team behaves in this network and relates to the final score of the game. Figure 3, which explains and shows the states of the Argentine and Spain in the connection between the entropy, which is actually the variety and unpredictability of the passings in the team performance. The more varied and the unpredictable team passes, the more points they tend to achieve in a score. This is because it's harder for the defending team to predict what will happen in the what will happen next, which helps the offense be more successful. Now coming to the second slide, which is the explanation of figure 4, looks how the score difference changes the team passing behavior. When a team has a small lead around let's say 3 to 9 point, they play with the most variety in their passing, high entropy, keeping the other team guessing. However, when a team is ahead by a lot or behind, their passing becomes more uh, predictable and low entropy. Ensure the team with a more varied passing patterns tend to score more points, and that behavior changes depending on that score. Team plays with the most unpredictability when the game is close, and the less when they are either ahead by a lot or losing a lot. Now about conclusion. Uh, Oberoi's research provides a valuable contribution to the field of dynamic graph in the analysis, offering a novel approach to detecting dynamic patterns within the complex evolving system. Thank you. This is all from our side.